Hello, my name is Matthew Rodriguez, and today I'll be presenting work that I did with my advisor, Michael Spear, on optimizing linearizable bulk operations on data structures. So first, a little bit of background. Concurrent data structures are important, and they're used in many real-world applications, but they are hard to design. In particular, bulk operations pose a significant scaling challenge, so it's typical to focus on performance of elemental operations, such as insert, remove, and contains. The simplest solution is two-phase locking, but two-phase locking is slow. It blocks access to many elements for a long time, and it makes many other threads wait. So first, let's discuss some other work that's been done in this space. One solution that already exists is the atomic snapshot. Basically, you create a snapshot of the entire data structure, which is atomic, so it represents the value essentially at one specific point in time, and then you do the bulk operation on that snapshot. While this works, it comes at a significant time and memory cost. It takes a while to build a snapshot, and you have to have a clone of the entire data structure. And staleness is a concern by the time the operation is done. The result might not be up to date. And finally, atomic snapshots are read-only, so it doesn't support mutating bulk operations. Another option is multi-versioning. Multi-versioning is essentially, it just keeps a lot of versions of each element. This comes again at a significant memory cost, and staleness is still a concern. And once again, there's no real support for mutating bulk operations. So that brings us to our contribution. We propose 3 algorithms which can be applied to different implementations of maps. These algorithms support linearizable bulk operations. So that means the entire bulk operation end-to-end is linearizable. So that doesn't mean each individual access by a bulk operation is linearizable. That means the entire thing is as though it was on an atomic snapshot. And since we're talking about linearizable bulk operations, it's important to quickly review what linearizability is. It's a strong correctness condition. For a sequence of events on a linearizable data structure to be correct, there must exist an equivalent sequential ordering. Not only that, but that sequential ordering must obey real-time order. If one operation started after another one ended, then they have to happen in that same order. You can't just flip them and say, okay, now it's going to some correct sequential ordering. No, it has to be in temporal order as well. When they overlap, then you've got a little bit of room to work with it. And finally, we want to meet some additional design constraints. We have a focus on system software, which means we want to obey strict memory bounds. We don't want any leaks, and we don't want memory leaks. We don't want to rely on a garbage collector. And we want to support mutating bulk operations. And we want to support bulk operations with loop carried data dependencies. This rules out a lot of potential solutions, such as parallelizing the bulk operation or using an atomic snapshot. If you've got mutating bulk operations and loop carried data dependencies, there's no way around going through each element one by one. And lastly, we want generic elements which are applicable to multiple different map and set implementations. So the primary underlying question that all of our algorithms seek to answer is, when does a thread need to delay in order to preserve the linearizability of ongoing bulk operations, including its own if it's executing one? All 3 of our algorithms answer the question using metadata about ongoing bulk operations. Where they differ is in the location and granularity of the metadata. Let's talk about both of those. There's two options with metadata granularity. There's low granularity, where the drawback there is a lack of information, and there's high granularity, where the drawback is there's more overhead. The second dimension we can vary is the location of the metadata. It can be global in some data structure shared by all threads, or local, as in it can be stored in the individual partitions of the data structure. With global, there's a greater risk of contention, but with local metadata, there's more overhead, and each thread has access to less metadata. Also, the metadata granularity is controlled by the number of partitions. So if you have partitions with 8 elements instead of 16 elements, well, then you have twice as much metadata. and the amount of metadata that's ideal for bulk operation performance may not be ideal for the overall performance of the data structure. So you might have to you might have to find some kind of compromise between those two. That's a drawback to local metadata. To understand the kinds of challenges our algorithms are trying to solve, we present this example of a cycle. In this example, we've got thread E for elemental, is performing two elemental operations, omega-1 and omega-2. And we've got thread F for for each, is performing a bulk operation, omega-F, which is a for each. A for each is a type of bulk operation that goes from the very beginning of the data structure, the bottom key, to the very end of the data structure, the top key. Due to the order of accesses on element E1, we have omega-F before omega-1, because omega-F is going from left to right, and so it's at E2 now, which means it has been to E1 and it's not yet at E3. So it has been to E1, and then thread E does omega-1 later. And so by the order of access to element 1, we have omega-F before omega-1. Similarly, on omega-3, thread E is already there. It's already doing omega-2, and omega-F is going to get there later. So we have omega-2 before omega-F. And lastly, due to the temporal ordering by having two operations performed by the same thread, we've got omega-1 before omega-2. That means we have omega-1 before 2, before F, before 1, which creates a cycle. So if this happens, there is no valid linearization of this sequence of events. This is not linearizable. In order to make this linearizable, we need to delay at least one of these ops. One of the key insights that inspired this project was noting that the cycle occurred because of thread E going from the left side of omega-F to the right side. Going from right to left does not cause a cycle. We can say that omega-F linearizes when thread E goes from the right side of omega-F to the left. So this gives us the idea that we can track the bulk operations linearization points. This is a bit of metadata that our algorithms can track in order to maintain linearizability. So that brings us to the first of our three algorithms, which we call aggressive ordering. Aggressive ordering uses coarse-grained global metadata. The advantage of aggressive ordering is that it's a simple algorithm with low overhead. It assigns a total global order to all bulk operations. And the bulk operations are ordered by their ID. And the IDs are assigned by their creation time. This means that bulk operations that start later are always ordered later. This presents the metadata that we use. We have a bit of global metadata where we have two atomic integers, the last ID and the linearized ID, and we have a bit of local metadata as well, where we have the last visitor ID embedded in the lock, as well as one bit just used to represent whether the partition is locked or not. So last ID is used to generate new bulk op IDs, and linearized ID is used to track which ops have been linearized, and each partition tracks the ID of the last partition, the last bulk operation that visited it. So under aggressive ordering, when a bulk operation proceeds, it obtains a unique ID called myID, and it will iterate over each partition in the data structure from bottom to top. For each one, it will wait until the last visitor ID is one less than its own ID, and then it will lock the partition, do the work, unlock, and atomically with the unlock, it will set the last visitor ID of the lock to its own ID. That lets everybody else know that, hey, I've been here, and the next bulk operation can go. When the bulk operation is finished, it will automatically increase linearized ID to myID if it has not already been increased to that value or a higher value, which might happen. What an elemental operation does is a little different. First, it gets the ID of the last linearized bulk op, which it calls last lin ID. It does this by atomically reading the global linearized ID value. Now, last lin ID represents the earliest linearization point for this elemental operation, but doesn't necessarily represent the actual linearization point. It can linearize later, but it can't linearize earlier. Then the elemental will find the partition P containing the sought key. It will wait until the partition's last visitor ID is greater than or equal to last lin ID, and then it will lock, do the work, and unlock. When it's done, it will atomically increase the linearized ID to the value that last visitor ID had when the lock was held. Despite its advantages, aggressive ordering does come with some drawbacks. Aggressive ordering means unnecessary ordering. It can't intelligently handle disjoint range operations or read-only bulk operations. Even though they don't need to be ordered, it will order them. Second, range operations must touch every partition in order to update that last visitor ID field. This is a pathology unique to aggressive ordering. None of our other algorithms suffer from it. And another thing is ordering by start time is not always the best. Sometimes you want to have a newer operation ordered before an older operation. So that brings us to our next algorithm, dynamic ordering. Dynamic ordering uses fine-grained global metadata, and it seeks to address the shortcomings in aggressive ordering by using more metadata. And the metadata object can be seen here. It consists of a list of sets of bulk op metadata objects, which store metadata on a single bulk operation each. Bulk ops in the same set are unordered with respect to each other, but bulk ops in different sets are ordered by the set's position in the list. Closer to the head is ordered earlier and vice versa. So what a bulk operation does under dynamic ordering when it wants to access a partition is first it will initialize the bulk op metadata object for this new bulk operation that's performing, and then it will insert it into the global list as early as possible. How this is achieved is complex and covered in more detail in the paper. Then it will iterate over each partition. It will first atomically search through the global list for any ops that block this op and acquire a lock on a partition if there aren't any. How that's actually implemented, again, is better than this, but this gets you the idea of how it works. Once it has a lock, it will do the work and release the lock. Finally, when the bulk operation is finished, it will recursively mark itself linearized. That means itself and any of its predecessors. And finally, it will remove its own metadata object from the global data structure. When an elemental operation wants to proceed under dynamic ordering, first it will atomically calculate a list of all preceding bulk operations, and it will determine which partition contains the key it wants to operate on. It will then wait until all the bulk operations in the list it calculated are done with that key. Once that happens, that means it's ready to go. It can acquire the partition lock and perform the operation. And finally, before it returns, it will linearize any bulk operations which have accessed K, and it will release the partition lock. Dynamic ordering avoids much of the false waiting incurred by aggressive ordering, but it does that by increasing the overhead by a significant amount, and now it has to deal with contention on global metadata. These accesses to global metadata are frequent and complex. Brings us to the last algorithm, localized ordering. Localized ordering uses fine-grained local metadata. It maintains the advantages that 2PL has on range operations, and it seeks to improve upon 2PL. So what 2PL does is it achieves linearizability by delaying operations from starting. This is just the simple operations of lock. If a lock is held, you can't begin to access that partition. However, localized ordering is built on the insight that it is sufficient to delay them from returning. So rather than a single lock, we have two queues. There's no global metadata. So any operation that wants to access an object first has to put itself into the started queue, and then wait until it has reached the head before it can access the object. This is a standard queue lock sort of implementation. But the new bit is the completed queue. Rather than simply returning when it's done, after it is done with operating with the object, it will put itself into the completed queue, and then it must wait until it reaches the head of that queue and dequeue itself before it can return. The completed queue increases the concurrency of 2PL without sacrificing the correctness. So without going into the exact details here, what each bulk operation does is it operates on each thread by enqueuing itself in the started queue, doing the work, and then enqueuing itself into the completed queue, and then moving on to the next partition. And then at the very end, what it does is it removes itself from all the completed queues. In this sense, it is still two-phase locking. There's the acquire phase where you put yourself in all the started queues, and then there's a release phase where you take yourself out of all the completed queues. What an elemental operation does is also pretty simple without going into the details. It just puts itself in the started queue, does the work, takes itself out of the started queue, puts itself in the finished queue, goes to the finished queue, and waits until it's ahead before it returns. So let's look at how these algorithms perform. In our evaluation, we look at these three algorithms as applied to two data structures. The first data structure is a chunk skip list of our own design, which is an ordered data structure. And the second is an interlocked hash table, which is an unordered data structure, which means that range operations cannot be performed efficiently on an IHT. Essentially what you do is just do a for each operation and check the range, whether it's in the range of the key. As a baseline, we compare against two-phase locking, and as an upper bound, we have an implementation where bulk operations are not linearizable, which we call NL in our charts. Now, the individual accesses are all linearizable, but the entire thing is not. It basically turns each bulk operation into a set of individually linearizable elemental operations. First is the Foreach-Only Workload. As we can see, aggressive ordering performs very well. It performs also as well as non-linearizable, but non-linearizable has a different correctness condition, so it's never going to do as well. The fact that it does almost as well is remarkable. In the range-only workload, with a short range length, unfortunately, we don't beat two-phase locking by much, except at 96 threads. But at a larger range length of 131,000 elements, we see that localized ordering is the best solution. It beats out the other two algorithms as well as 2PL, and it does about half as well as our non-linearizable upper bound. Lastly, we look at a mixed workload, which has both range for each operations and elemental operations in the case in the chart on the left, and elemental operations and range operations in the case on the right. And in both cases, we see that dynamic ordering performs the best. Now, this is just the elemental operations, but the throughput of the range operations in this chart is not interesting because it doesn't scale, because where the amount of for each threads or range threads is held constant. In conclusion, we introduced three algorithms for scalable linearizable bulk operations. We show that our performance exceeds two-phase locking, and we show that each algorithm has a niche, and no single one is the best. For more details, we ask that you please see the paper, especially there's a large discussion about partition size that was largely omitted from this talk. Thank you very much for your time.